ahead and share my screen and stuff, or
So let me introduce and then you start.
oh, okay.
Yeah. So hi everyone. This is the Ruby Junior Developer Book Club again. It's me, Nelson, and then Miles. And for today, Miles will be taking us through the session. Yeah.
Okay, cool. Hopefully I can share my screen without issue. It worked last time, so I think we're good. Okay. All right, cool. So this week's chapter is all about Ruby's hash table, which it uses for a whole bunch of stuff. It's kind of after the last chapter, I remember thinking, what other things are there to cover actually? Because we've covered so much material. So I didn't know there'd be a whole chapter on hash tables, but that's what we have here. And yeah, I guess I will start scrolling through here. Let's see. Some things I did take some notes on was, and I don't know if you guys felt this way too. Throughout the chapter, I noticed them saying a lot of things that were kind of sensitive to or are dependent on how the hash table is actually implemented. Um, Sort of, for example, he opens up here and mentions, unlike the simple array, hash tables can automatically expand to accommodate more values. Um, and so I assume he's talking about, in most hash table implementations, that is actually true, but it doesn't have to be true. So I don't know, that did come up occasionally throughout the chapter that I felt like he was talking very specifically of a particular hash table implementation. Um, and yeah, let's see. Chapter. Okay. Okay, so here we talk about how hash tables work. Things are organized into bins. Um, Not all hash tables actually have to work that way. I always wound up calling them buckets instead of bins, but maybe bins is the right term. Um, there's a type of hash that's pretty common to implement called an open address hash, and it doesn't really use bins, but it's still considered a hash table. So this was something that kind of felt a little strange to me that this feels like a very specific way to implement a hash table. So coming down here, so we have I don't know what type was. I don't think he explained this. We have the number of bins, the number of entries, and a pointer to the bins. One thing we learned a little later in the chapter is that it does use some metrics, which I assume it gets by dividing these numbers to figure out whether it should expand the hash table or not. So I think that's why num bins and num entries are there, or one of the reasons those are there. And maybe I should stop here and ask if you guys had any questions at this point in the chapter.
No, I didn't know that there were various ideas in implementing hash tables. I mean, he mentions that the specific implementation was not invented by Ruby, that it was taken from previous work, and then it was
Yeah,
just implemented in Ruby, just copied from the earlier. It was
yeah, I
very
can't
early,
remember.
right? Like 1970 something.
Yeah, it was either like I think it was said it was from Berkeley, so I guess we'll come across that at some point here. But yeah,
Yeah. Um, but yeah, I just don't know enough to know that like there were other
hmm.
options and this was one of the choices, or that this was the only choice that was available at the time that Ruby was written. Because Ruby's like from the mid 90s, right?
Yeah.
So
Well, this
maybe there's newer developments in hash table construction since.
Well, I mean, this choice of hash table is great, I think. It makes a ton of sense. It was really just the parts that I've learned, and perhaps I could be mistaken about this. The fact that you're hashing is crucial. It has to do that. So you have to be able to do the hash, you have to be able to look up, and you have to have some way of dealing with the collisions. Um, and that this is a way of doing that. But it doesn't have to be this way. But this is a great way to do it. It makes sense to do it this way. So not saying it. I definitely wasn't saying it was a bad hash table. It was just that I can't remember the terminology. There's like abstract data type and then there's data structure. Are you guys familiar with those terms? Like from, I don't know if you guys have had to learn computer science and stuff, but sometimes you have something where it's an abstract data type and then there's also the data structure, and the abstract data type is a little bit more about the interface and not so much lower level details. And then you have the data structure, which is kind of lower level. I almost feel like there's sort of an analog here where the hash table has certain properties and this structure has certain properties, but you can find hash table implementations that don't have this. Anyway, we should just go ahead and move on from that. It was just something that kind of stuck out to me. Um, Although here it does clarify a Ruby hash object with an empty hash table. Okay, so I'll go ahead and, oh, you know what? There is something, and I was going to mention this later. Um, One thing that I can tell has to be missing from here, and I don't know if you guys have noticed this, but I've leaned on this a couple times, is that the hash tables in Ruby are ordered now, and they weren't always ordered, but I think they became ordered probably in 1.9, certainly by 2. And in order to have the hash table ordered, there has to be some more information here that's missing. Because there's not enough information here to be able to get the elements back out in order. Um, I could kind of demo what I mean by that. Let me see.
Yeah, we that was covered in the previous book that we read. That
Oh, okay.
yeah, and the ordering is like it's unique to Ruby, right? Like it's uncommon that hashes are ordered.
Yeah, I don't usually think of a hash table as being ordered, but it's certainly convenient that it is ordered in Ruby. And I do like, it's funny, I can't think of a specific example, but in Ruby 1.8.7, there were situations where I kind of got in trouble because the keys weren't in guaranteed order and it caused a problem. So other people must have been running into that, including the Ruby core team, and they must have felt a need to make them ordered. I definitely like that they're ordered, and I can't even remember why. But there's not enough info here to print them out in order. So I wonder if there's just a pointer to an ordered list of keys that is missing here. So there's some detail that's missing there. There just has to be. Okay, so I'll keep scrolling here. Let's see what else I took notes on. Uh, oh, I went the wrong way.
Or maybe it became ordered in Ruby 2 and Ruby 1.9 just didn't have this yet.
That could be. Yeah, definitely by 2 they were ordered. I can't remember if 1.9 was ordered or not. Yeah, so we're coming on down here. Here we have a table entry, and then as we see later in the chapter, these form a linked list. So it looks like the table entry contains the key and contains the value. We have this internal hash function. This gives a number, which is then divided by the number of bins to figure out which bin to put it in. They store it in a variable called some value here for some reason. Okay, so now we're adding a second element to the hash table, and now it looks like this. So we have 11 bins here. 2 of them have 1 element in them, and the rest are all empty. Now he's talking about retrieving a value from the hash table. A great thing about hash tables is they have really fast lookups. Well, as long as the hash function is relatively fast and the hash function does a good job of evenly distributing the elements in the hash table, you should get really, really fast lookup times. So scrolling through here, length from hashes of varying sizes. He does an experiment here. Oh, here was that thing you were mentioning. So it was from Berkeley and it was in the 80s. So it looks like they just copy and pasted over that. And I think it says something about making some modifications to it. But yeah, it was apparently copied over from a really old implementation. We come down in here. He runs a bunch of code that inserts objects into hash tables of different sizes. I didn't really process this algorithm super in depth to make sense of it. He's doing something where he's making a decision about what to do based on, let's see, target key. Yeah, I didn't fully understand what he was getting at with this algorithm here. I guess yeah, I don't know what he was doing here. But anyway, the long story short there, he's trying to demonstrate that even in really gigantic hash tables, you get lookups that are comparable to really tiny hash tables. So that's just a pretty great thing about hash tables is that if they're well balanced and the hash function is fast, you can get the elements back out really quickly.
So I have a question. When you're comparing a hash and an array in terms of which is faster when you're retrieving data from it.
Well, again, that's kind of like the abstract data type versus the data structure, because if you look, this hash table is implemented using an array. So um, if you mean just storing elements in the array as if it were, I guess they call them vectors in Java. I don't know what the actual computer science term is for that concept, but uh, if you're just going to store elements randomly in an array and they're not sorted, then you have to look at on average half of the elements to find the one you're looking for. If they are sorted, you can divide and conquer. And then I don't know if you guys are familiar with that big O notation or whatever, but I think it becomes log of n. And hash tables, if they're working properly for all practical purposes, are considered big O of one, or it's supposed to be considered a constant lookup time, meaning as the collection gets bigger, the time it takes to look the data up stays constant. Um, so in an unsorted array, it's linear. You would expect a linear graph to go up like this. If they are sorted, you would expect like a logarithmic thing. So it would kind of, grow slowly, but it would grow. And then a hash table should more or less stay flat.
Yeah, maybe the next book should be data structures, because I'm familiar with data structures and algorithms, but I'm pretty sure Newton, you're not.
Yeah, I'm not.
Yeah, you know how
Yeah.
like you know how an old school phone book works, Newton, where like everyone's name is in the phone book by last name and you can find
Yeah.
them alphabetically? That would be like if you had a sorted array. And then if it were not sorted, you can imagine what a disaster that would be. You'd have to look through about half the book before you found what you were looking for. And then a hash table, I guess I can't really think of a good analogy there, but it'd be like you have a function that tells you exactly which page in line or at least which page what you're looking for is on, and you can jump straight to the page you want. So it's probably not a great analogy, but hopefully that gives a rough idea.
Yeah, I
Yeah.
mean, like
Yeah.
the way I first heard it was looking up a word in a dictionary, right? All the words in a dictionary are in order. So if you just open up the dictionary to the midpoint, like just open it up in half, is the word there? No. Is it bigger? Does the word alphabetically come before this point or after this point? And then you just keep dividing it in half. It ends up being a lot faster than trying to look it up in order by saying, okay, is it the first word? No. Is it the second word? No. Is it the third word? No. So
Yeah, yeah.
Okay. So another thing I wanted to maybe double check with you guys is when I was reading this chapter. Okay, my broad overview of what the chapter is about was like a hash is one of those things that make up Ruby as a language. So what we are looking at in this chapter is we are looking at how a hash object is implemented, like let me say at a lower level detail. I don't know if you guys got the same understanding when you're going through the chapter.
so the first part of what you said there, like the reason that we're studying hashes is because in our Ruby code, we use them a lot, but
Yeah.
also the C code that is used um, to build Ruby in the first place. uses hashes a lot. And so we're looking at it for both reasons. Uh, and we're looking at it to see why it's fast.
Yeah, one of the things I think that gets mentioned a few times in the chapter is that when you look up a method in a class when you're running Ruby, those are stored in hash tables as well. And I think he points that out in a couple places. So it's like you can have a class with a lot of methods, and it's important that you can find those methods quickly when you're executing Ruby code. And I think it mentioned constants. I think actually somewhere towards the beginning of the chapter, it even mentions other things that are implemented as hash tables that have already been covered earlier in the book, like looking up constants. Um, One aspect of looking up the instance variables uses a hash. I think it's in the class. It has some kind of way of mapping from an attribute name to the index in the array where it's supposed to be. So it sounds like hashes are kind of like used all over the place inside of Ruby, which is what
Mm.
Nelson was just mentioning. I
Yeah.
wouldn't say that it defines Ruby as a language per se. I have to assume that like JavaScript objects are hashes. Um, so I definitely Ruby makes use of hashes in a way that other languages, with the exception of JavaScript, maybe of the languages I've made heavy use of, like it has its own special clean syntax for it that a lot of other languages don't. Like in Smalltalk, the language that Ruby is descended from, it's not, I don't think it's as clean to create a hash. I'm actually not sure about that. Anyway, I suppose I should keep going. Uh, I guess I hadn't thought about that. I hadn't thought about hashes as a Ruby specific thing, but they definitely are dominant in Ruby. They're like a first class citizen in typical Ruby code, I would say. Okay, so we're adding a bunch more objects to a hash here, and he wants to go over how they expand. Oh, here he mentions hash collisions. So here's what that same hash table looks like after a ton of things have been added. We can see that the hashing algorithm is actually pretty good for these elements because the sizes only range from 3 to 5. So everything is nice and well balanced here. So the lookups should be pretty quick. But we are apparently at some kind of a boundary condition or getting close to one. Um, something important to point out here, there's an EQL method. There's like a few different concepts of quote unquote equality in Ruby, and one of them is this uh, .eql method, and that's what's used when there's a collision. If we're looking up an element by key, let's say we're looking up and the key is the string ABC and it hashes to some number. We divide it by 11 and we get 4. We know that the key value pair we want is in here. So we check is the key dot EQL question mark to this key, this one, this one, this one. And as soon as we get a true hit, then we're done looking. We found our entry in the hash table. So he's talking about hash collisions at this point in the conversation. Um, and he's mentioning these linked lists get longer and longer because he's leading up to, at some point, for performance reasons, we want to go ahead and expand the hash and increase the number of bins. And he's referring to that as rehashing. So up here we had 11 bins, and then down here we have, I guess, 19. And we've rehashed these entries. He gives some C code. I actually didn't read the C code because I just make an assumption of what happens. I'm assuming just like a new array of 19 buckets gets built. And I'm assuming we just go through one by one and reinsert them in this one. So I assume we have to rehash them and
Yeah,
then divide by
they're rehashed.
19. Yeah,
Yeah.
yeah. So
So the
um,
triggering condition for creating a new hash and a new set of bins is if the density exceeds 5. So on average, if we have,
on average.
yeah,
So like meaning I see. So this has a density of less than 5, apparently. This is probably closer to 4, right? In this
mhm,
drawing.
yeah,
But at some point it crosses that threshold and it'll rehash. One thing I hadn't thought of, and it makes sense, but I had never thought of it. They are intentionally using prime numbers. So 11's a prime number and then 19's a prime number. And it was just so that if the hashing algorithm is not good, dividing by a prime number increases the chances that you'll get a better distribution. Whereas if the hashing function is creating multiples of some number, like four or something like that, and then your hashing algorithm is divisible by four, you can wind up with not a very well balanced distribution. So that's interesting. I'd never thought of that before, but it makes sense. Another thing that surprised me about this, by the way, my inclination would have been to rehash this with enough buckets to have on average. I would have thought to rehash this to have a density of one after the fact. But Ruby doesn't do that, and this must just be way more performant. Um, it could be that the memory savings is more important than a slightly faster lookup of getting the density back down to one. Um,
Well,
so
it's a static algorithm that says, okay, I'm gonna grow the hash by an order of two.
yeah, which makes
So
sense. Just for whatever reason, my intuition, which is off for one reason or another. If there were, I think there was something like 66 objects or something in the array. I would have made something with like, I don't, is 67 prime? I don't know whatever number is prime that's near 67. My gut would have told me to expand this to 67 instead of 19. But that probably would use more memory than is desirable, and maybe that's why they don't do that. Um, but yeah,
well, I
okay,
mean, it did at first expand it to the next bigger one, and it will. So it's the closest prime to the next power of two.
yeah,
So so it's just gonna keep stepping up by powers of two, and it's I like I would assume that it would take more time to recalculate the exact number of bins that you want to make everything equal one. Like that would take longer to figure out than it would to just always go up by a power of two. And then, you don't have to make that decision. You don't have to do any additional calculation.
that could be. Yeah, I mean, you could also go by powers of four instead if you wanted to, and then that would get you closer to a density of one. But yeah, I just thought that was an interesting choice, and I wonder, um, yeah, that could be the rationale behind it. I'm just kind of it was interesting to me. Oh, here's where he shows the C code. I actually didn't really wind up reading this C code because I just assumed it did what we talked about before. Um, so I actually skimmed over this. So I'll keep scrolling if folks don't have comments on it. Um, so we have another experiment here. So he's inserting a new element into hashes of varying sizes. And I think this part was to show the cost of rehashing. Um, let's see. Okay, so if we come down here, we can see that it's getting slightly more expensive to insert as the hash is growing. It's still growing at a pretty slow pace, though. And then right here, and I guess this is around that 66 mark, where that density is hitting, I think Nelson mentioned five. Here's where it's deciding to rehash and expand the hash table. So it's basically stopping what it's doing, creating a new area in memory, and rehashing every element and writing it to the new bins.
Yeah. And I assume it also has to copy over all the previous values to
Yeah,
the new areas of memory.
yeah, yeah. Okay. All right. So he goes through explaining that. And here we get, he expands it out here to hit the next wall. So here we hit another expansion event where the Ruby runtime has to kind of basically focus on expanding the hash table. And that's why it's taking longer to insert this element. Oh, here's where he was talking about the prime numbers near powers of two. So that was interesting. Oh, and here's that density that you were mentioning, which is hard coded to 5. All right, so then we come down here and we're talking about implementing hash functions. Hash functions are pretty important for the hash table to actually function well. Here. I'm going to check my notes to see if I took any notes on this. I did not. Yeah. So I'll keep scrolling unless someone interrupts me with a question. Here we
Well,
see some. Go
I
ahead.
think it's important to note I don't know if it's here or further on, but like implementing the hash function means when he described it, it was like, okay, we're gonna take the value, the memory address for this object. We're gonna mix around the values in that memory address, and that's gonna become the hash.
Yeah. So that's the default hash implementation in object. I guess he has not gotten there yet. So I suppose
Oh,
that's
it's on
that must
page
be
183.
okay. That's coming up fast then. Here we see the hash algorithm for strings, and so hash and string must override the default because the default is going to give you the same hash if two objects have the exact same object ID. They have to be the same object in memory. That's the default behavior. Whereas a string, if you have two different strings in memory, but they both have the characters ABC, they will have the same hash value. So string hash must be an override of object hash. And so we could see these are coming out as integers. And it is interesting to see that if you really wanted to, a real fast hash algorithm for an integer is just return the integer itself. But instead, you get this giant thing based on that mixing that Nelson was just mentioning. And I'm assuming that this must just give you a better distribution in certain usage patterns. And then these
But
operations are going to be fast. So it's going to be doing some like low level bitwise manipulation of the numbers to get this data back really fast.
yeah, no, so the two strings ABC,
Mhm.
those are in two areas, two different areas of memory.
Well, one is ABD, one is
Oh, one is
ABD, and one is
ABD.
ABC.
Okay.
Yeah, they have like if you oops, thought that I wanted to open. Let's see. I'm not used to using GNOME, but if I do like S1 equals, and if you've used a hash table, you know that this has to be true because um, S1 to object ID. You get the when you put something in with a string, you can look it back up by a string with the same characters but different location of memory. So these you can see these two have different object IDs, but I can do hash s2 dot hash. So I do get the same hash back, even though these two have different object IDs. Wonder if I can do show sort. Do you guys ever do this? Source s1 dot hash. Okay, I don't have whatever is installed to do that, but you can sometimes see the source code for some of these methods. Although I guess that one's going to be in C code. But anyway, I'll hop back over to the Zoom call, which, oh no, I don't know where it is. So sorry, guys, I don't usually use GNOME, but I think I'm back. Uh, I'm stuck. So sorry, guys, I'm kind of stuck here. Oh, there we go. Let me close that. Okay, here we are. Sorry about that. So anyway, coming back over here, um, yeah, these are two different strings. And okay, so here's where he explains that the default behavior is to use object ID. Has murmur hash. So this is interesting. The hash function they used was invented in 2008. It's short for multiply and rotate. So it's doing some multiplication operation and then a rotate operation, which I'm assuming just is moving the bits around within the value of the integer. Objects as keys in a hash. So here he's going to start talking about, how you can write your own objects to use as keys in a hash or what goes into that. I guess before I move on, I should stop and see if there's any questions or comments about this stuff.
Yeah, I have a question.
Mhm.
So when you tried out the string example, this time by assigning a string to like a variable, you ended up
Uh-huh.
getting negatives, yeah, in the terminal. But then
Yeah.
when you look at the example in the book, it gives you
Yeah, I think
positive results for the very first two strings.
so. Something that I see every once in a while, I see Ruby programmers make this mistake. They'll use this hash as if it's a unique identifier for that object, which is a bad idea for two reasons. One of those reasons is that, as we saw earlier, there can be collisions. So even though collisions aren't good because they hurt performance, they are allowed. So that's one reason. The other reason is I'm pretty sure these numbers can change every time you start the Ruby runtime.
Yeah,
I think he mentions that
he,
somewhere
he
in
mentions
the
that. Yeah.
chapter. Yeah, so you do not want to use these, you don't want to use these hash values as if they are identifiers. They're not something you can use as an identifier to like retrieve a value in some other process at a different time. Um, they're also not identifiers anyway. Like even if they didn't change from program runs, there
Mm.
could be two different strings that have the same hash. It's unlikely, but it is allowed. So yeah, that is a problem I've seen before. I wonder if he should have mentioned that, or maybe he does. I'm not sure if he mentioned it. But sometimes people think that this can be used as an identifier, and it's not an identifier.
Yeah, it's the birthday problem. Like people underestimate how
Oh yeah,
many unique digits you need to make a collision. So I think it's like if you have 20 people in a room, there's a 90% chance that they're gonna share the same birthday. Like
yeah. I've
you,
heard that. I learned about that recently. Yeah,
it's counterintuitive. You know, it's 365 days. You think, oh, you need a lot more people, but it's uh, the math behind it is like, oh yeah, no, you need way fewer people than you think to create a collision.
yeah. All right, I'm going to keep moving along here. Okay, so here, oh, you know what? Oh, my internet connection is unstable. I thought it was actually Nelson's internet connection. I guess my internet connection is bad. Um, Sorry about that. So here we have a poor hashing function that's always returning four. Um, I totally forgot about this. I was going to look up a comic that I've seen before, and I think it's on that XKCD. So I'll share it in the chat like after, or maybe I'll go find it between the first and second segment. In fact, how are we doing on time? Do we need to switch to the
Six
other
minutes
meeting at
left.
6 minutes? Okay. So I'll go
Mm.
look for that. I'll go look for that image in between this. But there's something where someone needed to implement a random number, a function that returns a random number. So they roll a die and it comes up four. So they just hard code four in the function. So the function always returns four, even though it was determined randomly. And it just reminded me of that. It makes me wonder if that's why the author picked four, but it maybe it wasn't four. I'll go find the comic though. I totally forgot about that. So yeah, he wants to talk now about the impact of a poor hash function or method, I guess, since we're doing Ruby. Interestingly, here he writes equal, but he's overriding it and just calling super. So it's kind of this override is sort of pointless, but maybe he just wants to get us thinking about the equal method. And he's reusing his code from the earlier experiment. And that's when I had kind of wished I had paid better attention to understanding why he's doing this partitioning or whatever that's going on here. Um, but he's showing that here we have this flat structure here. And notice that we're not overwriting hash. Where he is going with this is that down here, he overrides hash to return four all the time. Something that is worth pointing out here that it's just an implementation of hash tables. If this equal function returns true for two objects, it's very important that they also have the same hash. Otherwise, you're going to break the way that hash tables work. So these functions have a relation, or these methods have a relationship with one another if you want it to be able to play nicely in a hash table. Okay, so now he goes through and does the experiment again, but this time with the lousy hash method. And we get this where just the performance is out the window. So this is actually Newton earlier when you were asking about an array. If you had an unsorted array you had to look through, this is what the graph would look like. Or as the structure grows, the time that it takes to look the stuff up is going up linearly. This doesn't look linear, and I think it's because this axis is logarithmic. So it's like this axis is linear and this axis is logarithmic. So this looks exponential, but this would be a linear growth relationship. So here with a good hash algorithm, we get a nice flat constant lookup time. And here we get a not so great linear lookup time.
Yeah, so when you're referring to a sorted array, is this like an array that's arranged in either descending or ascending order?
That would be sorted, yeah. This would be, these are, so if we scroll back up here, something to keep in mind is these are not sorted. And in fact, we can put objects in a hash table that might not even be able to be sorted. Like you can have objects for which the concept of sorting them isn't defined. So you're not even guaranteed to be able to sort these if you wanted to. But regardless, these are not sorted. So all you can do is this, does equal return true? Does equal return true? Does equal return true on the key value of all these? So all these entries have a key value pair. You're calling dot equal on the key value of all of these. And you have to keep doing that until you either hit true or you run out of items. It's even worse if the item's not there. Like if you're gonna look up, you're gonna get nil back if you look up a key that's not in the hash table. But to get that nil, you've exhausted every single object in the hash table before you can finally return nil. So that's like the worst case scenario, is the object's not even in there.
So an example of like an array that you can't sort is one that mixes, now let's say like numbers and letters. I imagine
That would be
it's a,
one, yeah.
yeah.
Yeah, that would be an example. I hadn't even thought of that, but that's true. These, because of the dynamic nature of Ruby and everything, these can all be actually different types. These don't have to be the same type. In fact, a common way that equal is taught, or that I remember equal being taught, was that this is like a stricter form of equality than the equals equals operator. And I find that kind of confusing. I think it's better to just say equal. I think it's better to just communicate equal in terms of hash table usage, but I think one of the differences of equal is that you'll get false if they are of different type, whereas equals equals can sometimes return true, just depending. But I don't really personally like to think of equal that way. I really just like to think of equal as being defined so that a method, or that an object can behave as a key in a hash table correctly, is the way I like to think of the equal method. Otherwise, I get confused.
We have 40 seconds.
Okay, maybe we should kill it here and jump over to the other meeting.
Yeah.
Okay. All right. See you guys over there.